Well, today I want to continue reviewing integration techniques. So this is kind of like the outline that we're going to do. We have the power rule, we have U-substitution type problems, then we have some integration by parts, and then with that, I'm going to talk about something called the hidden value and the tabular method. Some people call it something different. I believe people call it the tic-tac-toe method. Some people call it the tabular method, and then some people call it the I-late method, I believe. But tabular method, we'll just keep it like that. Then we'll talk about using long division when it comes to integration with some partial fractions, and then we'll top it off with completing the square and give you some examples of arctan and then natural log solutions. Again, I don't expect you to know any of these methods here. However, if you don't feel comfortable with any of them, you're more than welcome to let me know in the chat. We'll love to know what your strength is when it comes to integration. Are you a beginner, or are you just here for some math fun? So anyway, let's go ahead and get started with the power rule. So as you recall, we're going to have an integral, and I'm just going to go ahead and write out a basic one. Let's just say I have the integral of x cubed dx. And there's many applications to this, but today all we're focused on is just how do we solve for this? How do we find the antiderivative? And the very first thing that we want to go ahead and start doing is the power rule. And if you recall, the power rule is kind of like a differentiation, but we're just working backwards. We're going to go ahead and add 1 to the power. In this case, the power was 3, so we're going to add 1 to that. So we have x3 and then plus 1. And we're going to divide by the new power that we have. And in this case, it's going to be 4, because 3 plus 1 was 4. And we always need to make sure that we include the plus c. I'm curious what the chat has to say about that. Why is it that we add a plus c? Go ahead and let me know in the chat why you think that is. But this is essentially the most basic integral that we can have where we implement the power rule. There's going to be different instances that we are going to cover when it comes to this. And one of them could involve radicals. So let's just say, for example, we have a radical or root x. So if you have a problem like this, we have to make sure that we rewrite the power. And we rewrite that as x to the 1/2 dx. And now check this out. We're going to go ahead and add 1 to the power. So it's going to be x to the power of 1/2 plus 1. And we're going to divide by the new power. I'm just going to kind of show all the work here. I'm going to do 1/2 plus 1. And this is where you have to be very careful with your fractions. Up on top, we have a 1/2 plus 1. That's going to become a 3/2. And in the bottom, same thing, 3/2. So as I mentioned, not only do you have to know, or you have to be comfortable on adding your fractions here, but you also have to be very comfortable on dividing your fractions, because if you see, we have an x to the 3/2 on top and then a 3/2 on the bottom that's being divided. So I'll kind of let you think about how we get this answer, but this is going to be 2/3 x to the 3/2 plus c. Another basic integral that we should know about. All right, and then from there, let's go ahead and just change it up real quick. So how about having something on the base? So we have 1 over x to the 4th, for example. Another basic integral where we're going to use the power rule, but in this case, the x to the 4th is on the bottom. So what we're going to do is go ahead and move it to the top. And we do that by rewriting this as x to the -4. That's it. And from here, we're just going to go ahead and continue implementing the power rule. And we're going to go ahead and add 1 to the power plus 1. Or actually, let me just go ahead and rewrite that. X to the -4 plus 1 over -4 plus 1. Okay, so we have x to the -3rd over -3. And obviously, we have the plus c. And now I can go ahead and rewrite that. The only thing that's going to change is that x to the -3rd, because it has a negative power. So we're going to go ahead and bring that down. So this is going to become 1 over -3x cubed plus c. The basic power rules that we should know. One, it's the basic x squared, x cubed, x to the 5th, whatever it might be. Then we have the root, which we just did. And now we have this one where we have something on the bottom. So these are the basic ones that we should know about. And obviously, I'm hoping that if you're joining, you probably know this. Okay, well, now let's go ahead and talk about U-sub. U-substitution. Now, what happens, this is almost like a reverse chain rule. type problem. So let's just say, for example, I have something like 3 to the 4x minus 1 to the power of 6 dx. Now, this one's a little tricky because now what we have is we have something within this parentheses. And sure, we can go ahead and integrate this. We can go ahead and add the power, but it's going to become somewhat confusing because it's not, this is not going to be, and I repeat, this is not equal to 4x minus 1 to the power of 7 over 7. That's not going to happen. If you were to check this, if you were to take the chain rule of this, then what you would get, or if you were to take the derivative of this, then you will get 21 4x minus 1 to the power of 6 over 7 times the derivative of what's inside, which is going to be 4. And that's not going to simplify. This is going to become 12 4x minus 1 to the power of 6. So this is not the same as our original equation, but it's close, right? As you can see, we have a 12 and the other one had a 3, so we have to do something with that. So this is where we go ahead and use U-sub. We're going to try to rewrite this. Actually, let me just go ahead and erase the portions that I had here. We're going to go ahead and try to rewrite this by making our value in here our U. And every time we do that, we have to make sure, because it looks like we're planning to rewrite our equation in terms of U. So because we have a dx, we need to find the du. We need to find out what that would be. So all we have to do is, with our u value, we're going to go ahead and integrate, differentiate both sides. This is going to become du is equal to 4 dx. And you have to make sure you include the dx on the other side. It's almost like implicit differentiation here. Then we can go ahead and divide the 4 so we can isolate this dx value. And we have du over 4 is equal to dx. And this is perfect because check out what we're going to have. We're going to rewrite our integral. We still have 3. And as we mentioned, we make that entire parentheses our u, so that's u to the 6th, times du over 4. That was our dx value. And now let's kind of simplify this before we continue. The 3 and the 4 I can kind of bring together. One's a numerator, the other's a denominator. So this is really 3/4 u to the 6th du. And now we just have a classic u, or a classic power rule problem. And this is why I mentioned that we need to obviously know that. So this is going to become 3/4 u to the 7th divided by 7. Obviously, now we get the plus c, and this becomes 3 u to the 7th over 28 plus c. Now, I kind of circled this and said, okay, this is my final solution, but this is incorrect. Go ahead and let me know in the chat why you think this is going to be incorrect. And it looks like our solution is still in terms of u, so we can have that. All right, so we need to make sure that we rewrite this back in terms of x. And how do we do that? Well, all we need to do is find what the u value was. I highlighted that over there, but now on top, check that out. We already know that u is equal to 4x minus 1, so we can go ahead and plug that back in. So now we have our real solution is 3 parentheses 4x minus 1 to the power of 7 over 28 plus c. So if you think back of the example that I gave you in the beginning of this problem, where I said, oh, we can just implement the power rule, we were very close to what the answer will look like. But it was missing just a little something there. And it was for us to find the u value, find the du, and then that 4 in the denominator was missing. So that's U-substitution. I have a feeling you're going to get more comfortable with these as you go along. U-substitution will be almost second nature to you as you do these. Okay, well, let's try a different U-substitution. Now what happens when we have, let's just say, for example, square root of 3x squared plus 1, and then we'll put an x on the outside. Okay, this looks even more confusing. But again, with a problem like this, it's all about going down the list. We had power rule. It's not going to work in this case. So maybe U-substitution is going to work. I like that. So now what we're going to have is we're first going to rewrite this as x and then 3x squared plus 1 to the power of 1/2 dx. And check this out. We're going to make this inside value our u. So u is equal to 3x squared plus 1. And du is equal to 6x dx. That's real nice. And so now we can go ahead and divide the 6x to the other side. And we have that du over 6x is equal to dx. And now we can go ahead and rewrite that integral that we had. So this becomes x times, don't forget that was our u value, so we have u to the 1/2, times our dx, which is du over 6x. And this is beautiful because we can go ahead and cancel out the x on the top and the bottom. That 6, don't forget, I'm going to go ahead and kind of put it on the outside, but 6 is a denominator. So this is going to become 1/6 on the outside, integral of u to the 1/2 du. And this is very similar to the first integral that we did in the, or I will say the second integral that we did when it came to the power rule. We're just going to add 1 to the power and then divide by the new power. So that'll be 1/6 times u to the 3/2 over 3/2 plus c. Let's rewrite this just a tiny bit. And now we have 1/6 times 2/3 u to the 3/2 plus c. And I'm going to do two things at the same time. First, we're going to simplify that 1/6 times 2/3. And that will be 1/9. And then I'm going to go ahead and just plug in the value for u that I had on top back into my integral. And that's going to be 3x squared plus 1 to the 3/2 plus c. You're probably looking at this and thinking, okay, I definitely need to work on my algebra. And to be honest, it's probably the hardest part of calculus. It's not necessarily the calculus portion. We all know how to do integration. I mean, it's a very simple concept. It's just the algebra, keeping up with our fractions and making sure we're keeping tabs of all of our numbers. That's the hardest part, in my opinion. All right, well, let's do one more U-substitution. Now what happens when we have, let's just say this is an 8x over 12x squared plus 1. Again, a little different. Okay, now keep in mind, in this case, the denominator has a larger degree than the numerator. I'm saying that because I'm going to kind of preface that with a different example that we're going to do later on. And what we're going to do is, again, make the bottom value our u. U is equal to 12x squared plus 1. Our du is going to equal to 24x dx. And now we're going to go ahead and divide the 24x to the other side. So that we have du over 24x is equal to dx. And that's how we're going to rewrite our integral that's on the left side. So we have 8x over that entire denominator was our u value times, and then the dx is now going to be rewritten with the du over 24x. And now we just have to simplify a few things. The x's cancel out, as you can tell. The 8 and the 24 can go on the outside. 8 is a numerator, 24 is a denominator, but that can simplify into a nice fraction that's just going to be 1/3 integral of 1 over u du. Now, this integral here is a very basic integral that we should know. Every time you have 1 over u, that's just equivalent to the natural log of u. So this is 1/3 natural log of absolute value of u plus c. And our last step is just to go ahead and rewrite this in terms of x. So we plug in the value of u that we had on top in for the value of u into the integral. So now we have 12x squared plus 1 plus c. That's it. Awesome. Okay, so that's the 3 basic type of situations that you can have when it comes to U-substitution. Obviously, there's so many complex integrals that are out there, but this is all about just learning some of the basic techniques so that when you arrive or you see different integrals, you can kind of think about the process of what method we can actually use. So far, we've only done power rule. We've done U-substitution. Well, now we're going to do integration by parts. And integration by parts definitely looks a little scary. And I don't know, again, let me know in the chat if you've heard about integration by parts, or if this is the first time hearing about it. But I'm going to kind of just introduce this very quickly. So you have an integral where you can make one value your u, and now we have a different scenario where we're going to make our other value our dv, and we'll talk about how we're going to derive those things. But if you have that perfect situation, we can go ahead and rewrite our integral as this. And it might look a little more complex, but you're going to see that it's going to be a lot easier for us to integrate this. And this is going to become that uv, or u times v, minus integral of v du. So let's go ahead and look at some examples here that we can do. So let's go ahead and try an integral that might look like this. Let's do okay, let's start off with something like this. Integral of x sine of 2x dx. Okay, so now we're getting to the integrals of trig functions. And I'm hoping, I know we're not covering them really today, but I'm hoping that you maybe know the basic integrations for sine, cosine, and tangent, perhaps secant squared and all that. So when you have a problem like this, again, you can't do U-substitution, you can't do power rule, so we have to go to the integration by parts. And the best way to approach this is to make our u value something that we can easily take the derivative of, and hopefully our derivative becomes somewhat nice. This is what I mean by that. So our u value is going to be x, and our du is going to be the derivative of that, which is just 1, and then dx. And now we have the sine of 2x. That's our dv. Okay? Actually, I should have done this as that's our dx right there. Okay? And now we're going to go ahead and take the integral of this. So we kind of have to work backwards. And that's something that we can easily integrate. That's just going to be negative 1/2 cosine of 2x. And as I mentioned, this is something that you kind of have to be aware of some basic trig examples or trig integrals here. And now we can go ahead and rewrite this using that uv minus v du. So let's start off with our u, that's x, times our v, which is negative 1/2 cosine of 2x, minus integral of our v value, which is negative 1/2 cosine of 2x, times our du, and that's just the dx. Now let's go ahead and rewrite this. This becomes that first term. I'm just going to multiply the negative 1/2 times the x. This becomes negative 1/2 x cosine of 2x. And then this second part, the second term, notice that there's two negative signs there. So it's obviously going to become a positive. And I'm going to bring the 1/2 on the outside as well. So this is going to be plus 1/2 integral of cosine of 2x. And the thing about integration by parts is that, yes, it looks a little complicated. This is the only way that we can solve this. And if that's the case, we're just going to have to integrate that last part. And that's still pretty simple. Plus 1/2. And then now this is going to become sine of 2x over 2. And now we have the plus c. Let's go ahead and create some space here on the blackboard. I don't know if any of you follow me on TikTok, but as you already know, whenever we go live, we are always trying to make space on the blackboard because things get crazy when it comes to that, when it comes to problems like these, at least. Okay, so now this is going to become negative 1/2 x cosine of 2x plus 1/4 sine of 2x plus c. And now we have our integral. A little more complicated than U-substitution, a lot more complicated than power rule, but that's the only way that we can solve this type of problem. That is integration by parts. Okay, so now let's talk about integration by parts, but now let's talk about when we have something called the hidden value. So let's just say, for example, I'm just going to kind of leave the integral here. U dv is equal to uv minus integral v du. Okay. Well, let's talk about what happens when you have an integral of something like this, natural log of x. We can't really solve this, or at least we don't know the integral of this. A lot of people are probably going to already tell you what the integral of this is going to be. It's because they have it memorized. But in this case, we still want to use, we're going to use integration by parts, but this is what I mean by the hidden value. Okay, so we need to pick something for our u. Our u is the hidden value that's right out front of the natural log, and that's going to be 1. Actually, we're going to change that up. Our hidden value is going to be our dv. So first, we're just going to go ahead and start off by making our u equal to ln of x. So u is equal to natural log of x. du is equal to 1 over x dx. And then our dv is just going to be the dx. And then technically what you have is you have a 1 on the outside. So it's going to be a 1 dx. So dv is equal to 1 dx. And v is the integral of that. So now we're going to make that x. And if we're using the uv minus v du, which is the integration by parts, we're going to go ahead and do u, so natural log of x, times v, which is x, minus the integral of v, which is x, times du, which in this case, it's going to be 1 over x dx. So let's simplify this. The first term, I'm just going to kind of rewrite. I'm going to do x natural log of x minus integral of, you'll notice that the x and the 1 over x cancels out. So you're just left with 1 dx. And now it's our job just to integrate that last part, which is just going to be x, and we have plus c. So this is a solution to the integral of natural log of x. One way we could also rewrite it is we can factor out the x and do natural log of x minus 1 in the parentheses. So that's one way of doing it as well. So this is what happens. Again, another integration by parts example where you have to, again, I call it the hidden value because you don't really see what the dv is going to be, but it's just going to be the dx and then with the 1 on the outside. So now what happens when you have something, or when we're going to use the tabular method? The tabular method is just a nice little shortcut to integration by parts, especially when you have to constantly do it. So the way it works is, if you have a problem, even as easy as x squared cosine of 3x dx. If I were to use U-Substitution or integration by parts here, you will notice that we're going to have to do this multiple times. Let me quickly show you here. So I make my u equal to x squared, du is equal to 2x dx, and then my dv is equal to cosine of 3x dx, and then our v is going to be 1/3 sine of 3x. And so when I use integration by parts, I'm left with 1/3 x squared sine of 3x minus integral of 1/3 sine of 3x times 2x dx. So if I rewrite this, this becomes minus 2/3 integral of x sine of 3x. Now we still have to integrate this part, and the way we do that is using integration by parts again. So as you can see, it just gets a little messy. So the way we can recognize that we're going to use the tabular method is, one, obviously it's going to be integration by parts, but more importantly, if you can get your u to be something that we can take the derivative of constantly and finally get 0, then we can use tabular method. Let me show you what I mean. Again, instead of doing this whole thing, which you can, there's nothing wrong with that, I'm going to show you how the tabular method is going to work. And typically it becomes, or you can use this for these types of integrals here, where you have like an x squared or an x to the 5th or anything where you can take the derivative and eventually get 0. So if I start off again, I'm just going to rewrite that. So our u is going to be the x squared. So that's my x squared. Let's go ahead and take the derivative until we continue to get 0. So it's only 4 terms, not bad. And now our dv is going to be the cosine of 3x, and we're going to integrate this. So this is going to become 1/3 sine of 3x. And we have to integrate again. This is going to become negative 1/9 cosine of 3x. And integrate one more time. Negative 1/27 sine of 3x. And the tabular method tells us that before we even continue, we need to write the signs on the left side here. So you always do plus, minus, plus, minus. You continue alternating, but you always start as a plus. And then now our solutions are going to be the product of this value, which is x squared times 1/3 sine of 3x, times this value. You notice that it's kind of like a diagonal. You start with the plus, go to the x squared, then you work your way down. So that's going to be minus 2x times negative 1/9 cosine of 3x. Don't worry, we're going to simplify that in a second. And then the last one is the last product here. So times that value there. And it looks like it's plus 2 times negative 1/27 sine of 3x. And then we have our plus c. So let's go ahead and simplify this. This becomes 1/3 x squared sine of 3x. This second term, there's two negatives there. So this is just going to become plus 2/9 x cosine of 3x. And then this last part is going to become minus 2/27 sine of 3x plus c. That's the tabular method. Could you imagine trying to do integration by parts? It looks like you were going to have to do it, well, I guess 2 times in this case, which isn't too bad. But if you were to have a problem, I'll write it here on the top right. If you had a problem like this, integral of x to the 5th sine of x, even just that alone, doing integration by parts will take you a long time. So it's probably best to just go ahead and use tabular method. So those are the little tricks when it comes to integration by parts. I hope you enjoy on that. Okay, so now let's go ahead and talk about some long division. So if we're talking about long division, obviously we're dividing some polynomials. So our integrals are going to look a little bit like this. X cubed plus 2x squared minus 3x plus 1 all over x plus 2, for example. Okay. Now, obviously a little different from, I believe, one of the problems that we did with U-Substitution. Not only is this longer, but at the same time, look at the degree of the top and on the bottom. In this case, the top has a degree that's larger than the bottom. So it looks like we have degree 3 on top and we have degree 1 on the bottom. And when that happens, that's where we can go ahead and use U-Substitution, long division, and then we can go ahead and see what our result is and go ahead and integrate that. So let's go ahead and just show the long division. You could honestly do synthetic if you wanted to, but I'm just going to show all the work here. So you're dividing the numerator by the denominator, and now you just have to kind of do the long division. If you don't remember this is something that you should definitely look back on and just practice, because it does show up a few times whenever you're doing integration. So this is going to be, let's see, x squared, and this becomes x cubed plus 2x squared. We subtract these two. Oh, this is beautiful. Now we have minus 3. So then we have negative 3x minus 6. Subtract these two, and that becomes 7. So we have a remainder 7. So our answer for this whole thing so far is going to be integral of x squared minus 3 plus 7 over x plus 2 dx. And this is really nice because now we can split this up into 3 different integrals. You probably don't have to. If you can already see the solution here, then that's great. Otherwise, go ahead and split it up. That first integral is just using power rule. So x cubed over 3 minus the second one, which is going to just be 3x. This last one is basically a U-substitution problem where u is equal to x plus 2, du is equal to dx. So then this becomes plus 7 integral of 7. Oh, I'm sorry, you already have the 7 there. 1 over u du. And if you recall, the integral of 1 over u is just a natural log. So this is why it's good to kind of memorize this, because this is just going to become plus 7 natural log of our u value, which was x plus 2, and then plus c. Really nice. Really, really nice. Again, this is a long division type problem. So whenever the numerator is larger than the denominator, you're just going to go ahead and use long division. Now let's go ahead and jump to a different example. Let's go ahead and talk about when the numerator is not larger than the denominator, meaning in terms of degrees. So what's going to happen when we have a problem? Let's just say let's go ahead and do a problem that might look like this. Integral of x plus 5 over x squared plus x minus 2 dx. So as you can see, the numerator is not larger than the denominator. In this case, the degree of the bottom is larger. So we have to try something else. So this is where our journey with partial fractions is going to start. And there's so many things that we can dive into when it comes to partial fractions. But first, I'm just going to go ahead and show you one example, and then we'll continue with other situations. Again, this is just a webinar, but I will definitely continue doing more in-depth videos on stuff like this. So when it comes to partial fractions, again, we can use long division. So we're going to go ahead and factor out the bottom. This is going to become x plus 2, x minus 1. As I mentioned before, we have to make sure that we understand our algebra. That's the hardest part. And the idea is that, okay, well, since we have two factors on the bottom, we can go ahead and rewrite this as some value a over x plus 2 and b over x minus 1. Now, the rule here is that the top has to be 1 degree less than the bottom. So since x plus 2 has degree 1, then the bottom, or the top, the numerator in this case, has to be degree 0. So it's just going to be a constant. If it was a quadratic, I'm just going to give you that situation. If it was like, let's just say, for example, the denominator was x squared plus 1, then in the top, we were going to have to include an ax plus b. So again, it has to be 1 degree less than what it was on the bottom. Partial fractions, there are so many things that we can dive into, but this is just a surface level example of what you can do when you have these types of problems. And so now the idea is like, okay, if we were to combine these using common denominators, that first fraction, we would have to multiply an x minus 1 to the top and the bottom. And the top fraction, or the second fraction, we will multiply an x plus 2. And so this is going to become a times x minus 1 plus b times x plus 2 all over x plus 2 x minus 1. And now we succeeded because now we have the same denominator on the bottom as the integral that we have. That means that our numerator has to equal to x plus 5. So this is where we have to do some investigating. We're going to go ahead and take the numerators and just set them equal to each other. Because now we're going to do x plus 5 equals a times x minus 1 plus b times x plus 2. And there's a ton of ways of solving these types of problems. One of them, it's called the cover-up method. And the way they do this is they want you to think of what can I plug into one of the parentheses on the right side so that they cancel out. For example, if I plug in x is equal to 1 into the equation, well, I'm going to get 1 plus 5 equals a times 1 minus 1 plus b times 1 plus 2. You notice what happens to that a value? In the parentheses, we get 1 minus 1, which is 0, so that cancels out. Didn't want to erase it there. There you go. So that cancels out. And that's really nice because now we have 6 on the left side, and then we have b times 3, which tells us that b is equal to 2. Let me go ahead and create some space here on the blackboard so I can move some stuff around. But that's the cover-up method. Again, it's really nice to think about, okay, well, so what can I plug into the parentheses so stuff can cancel out? And we're going to do the same thing for the other parentheses. Well, how about if I plug in negative 2? So that's negative 2 plus 5 equals a times negative 2 minus 1 plus, we already know the b value is 2, so I'm just going to put 2 there, but then negative 2 plus 2. That's okay, because this cancels out. I don't care about that anymore. So now what we have is negative or positive 3 equals negative 3a. And that tells me that negative 1 is equal to a. And so now we can rewrite this entire thing. Let's make it smaller. Actually, let's just move it on this side. And so now we can rewrite, as I mentioned, the integral of x plus 5 over x plus 2 times x minus 1 dx was equal to some a over x plus 2 plus b over x minus 1. Well, now we know that this is going to become our a value, which is negative 1 over x plus 2, plus our b value, which is 2 over x minus 1. That's really nice. That's really nice. And so all we have to do now is integrate these. And we can separate it into two different integrals. And if you recall, I believe from the other example, this is just a U-substitution that's going to be a natural log. So this becomes negative 1 natural log of x plus 2 plus 2 natural log of x minus 1. I can't emphasize it enough that you gotta practice your natural log integral, because that shows up a lot. And it saves you a lot of time by not doing U-substitution every single time. So this is one example of partial fraction decomposition. Definitely looks a little more complicated, but the more you practice it, the better you would get. So we talked about long division, we talked about partial fractions, and now we're going to talk about two different situations, and these will be the last two methods before we end the webinar. And the first one's going to be an arctan problem. So if you recall, this is something that shows up a lot. We can have a situation that looks like this: 1 over x squared plus 1. Or actually, I'm just going to call it plus a squared. This is a very special integral. Shows up many, many times, and you're going to see the more you do it, the more you'll see arctan. This is equal to 1 over a arctan of x over a plus c. Now, let me give you some examples. What would happen if I have this x squared plus 9? Well, we're going to have to rewrite this so that we can do this, x squared plus 3 squared. Notice that I kind of rewrote it so that it can look like the general integral that I had on the top left. Our x is fine, and our a value in this case is 3, because a squared, 3 squared, is 9. And so now we can go ahead and say that this integral is 1 over the a value, which is 3, arctan of x over 3 plus c. And this shows up numerous times. But now, let me go ahead and show you a different problem. This is the arctan, but what happens when you have, this is the ln. What happens when you have 1 over x squared minus a squared, for example? Go ahead and let me know in the chat what you think that is. Or again, if you haven't covered it, that's totally fine. What this is going to become is this: 1/2. Well, actually, I'm just going to, it's an a value. So 1 over 2a natural log of x minus a over x plus a. There's a whole work around this, but for today, I just kind of want to talk about those basic integrals. So they look very similar. One of them is x squared plus a squared. The other one is x squared minus a squared. So you can definitely solve this. The bottom one, you can solve it using partial fractions because you can factor it out because it is a difference of squares. But this is a general solution. Again, this is something that you see a lot. This is something that you'll see constantly when it comes to these integral problems. So let me go ahead and just create some space on the blackboard here. So I could then, whoops, not what I wanted. So what happens if I have an example integral of 1 over x squared minus 16, for example? Well, if I rewrite this, this is 1 over x squared minus 4 squared. And now we can go ahead and just implement that rule that we have there. This is 1 over 2 times our a value is 4 in this case. So this is going to be 4 natural log of x minus 4 over x plus 4. And then don't forget the plus c. So if we rewrite this as 1 over 8 natural log of x minus 4 over x plus 4 plus c. Again, two very unique integrals that we should know. One of them is the arctan, and the other one I just call it the ln. So it's a difference of squares. Saves you a lot of time if you don't want to use partial fractions. So I think it's always good to know this integral here. So now this is a very basic one. In here, everything was just x squared plus 9, x squared minus 16. Very simple. But what happens when you have a problem that looks like this? Let me go ahead and use yellow. I'm sorry about that. So what happens when you have a problem that looks like this? 1 over x squared plus 6x minus 1, for example. So we can go down the list. Not power rule. We can use U-Substitution. There's no way that we can use integration by parts. We can try long division. Doesn't work because the numerator is not larger than a denominator. We can try partial fractions. We can go ahead and factor this. But I want you to think about, how can we factor this? Is there something that multiplies to -1 and adds to 6? There isn't. Okay, so it looks like we're almost running out of options. Well, this is where we have to revisit the completing the square. And I hate this method so much. I just don't like the way mentally it makes me feel, but I know that it's super important when it comes to integration or really just in higher level math. So we're going to complete the square here because we couldn't do anything else. And how do we do that? Don't forget, we take the 6, we divide it by 2 and square it. So you're taking the b value, dividing it by 2, and then squaring it. So this becomes 9. And so we're going to introduce a 9. And we still have the -1. But don't forget, but because we introduced the 9, we have to subtract the 9. And so now what we have is an integral that looks like this. 1 over x squared plus 6x plus 9. And then the -10. So we're going to go ahead and factor that out. And now this is going to become 1 over x plus 3 squared minus 10 dx. This is real nice because look at this. It looks very similar to one of the other problems that we had done. This looks very similar to this. 1 over x squared minus a squared. And that's exactly what it is. But before we do that, we need to kind of just set it up that way. So first, we're going to make our u equal to x plus 3. So our du is just dx. And don't forget, a squared was equal to 10. That means that a is equal to root 10. It's a little tricky here because we have these radicals. And so this whole thing is just going to become integral of 1 over u squared minus root 10 squared times du. And if you recall, the integral or the solution to this, let me go ahead and write it here in red. When we had 1 over x squared minus a squared, we said this was 1/2 a natural log of x minus a over x plus a plus c. Okay. Well, in this case, we're just going to, instead of x, we're going to put u, and instead of a, we're going to put root 10. So now this is going to become 1 over 2 root 10 natural log of our u minus root 10 over our u plus root 10 plus c. But we're not done yet. Why? Because this is still in terms of u, so we need to rewrite this in terms of x. So let's go ahead and do that now. This will be our last step. And we have 1 over 2 root 10 natural log of x plus 3 minus root 10 over x plus 3 plus root 10. And that is that basic integral. So it's really nice, again, when we couldn't do partial fractions, we went to completing the square. We found that this was a difference of squares, and then now we were able to find a nice solution to this integral. Well, this was the natural log one. This was a difference of squares in the bottom. What happens when you have a plus instead of a minus? Well, let's go ahead and explore that a little bit. So we're going to have 1 over x squared plus 8x so let's do plus 20 there. There you go. So again, we practice this. Okay, we look at this. We can use long division. Could we use a partial fraction decomposition here? Something that multiplies to 20 and adds to 8. That's definitely 10 and 2, but that can add to positive 8. It will subtract 2 somehow, but then that would mean that that had to be a negative 20. So we can't really do anything about this. So we're going to have to go ahead and complete the square. So here we go. We're going to go ahead and take the 8, remember, divide it by 2, and then square it. That's going to be 16. So we introduce the 16, and then we have the plus 20. And because we introduced the 16, we're going to go ahead and subtract the 16. And what we're left with is an integral of 1 over x squared plus 8x plus 16, and then plus 4. And if we continue to simplify this, we can go ahead and factor out that quadratic, which is exactly what we want. And this is x plus 4 squared plus 4 dx. And if you recall, I'll put this in red here, that the integral of 1 over x squared plus a squared dx is equal to 1 over a arctan of x over a, and then plus c. Now, this is very similar to that because we have the plus 4, but we need to rewrite this a little bit. So we make our u equal to x plus 4. Our du is dx. And then don't forget that our a squared was 4, so our a becomes 2. And so now we can rewrite this as integral of 1 over u squared plus 2 squared du. And now that looks very similar to the integral that I have there in red. So now we can just do 1 over our a value, which is 2, arctan of u over 2 plus c. And now one last step. Let's go ahead and rewrite this now in terms of x. So we bring back the x plus 4, substitute it in for the u, and now we have the solution to our integral. That was arctan, and that was the Ln type integral. Let me know in the chat what other integrals you think we could also learn next time. But that's going to do it for today. Again, I am so thankful that you guys logged on to the first ever webinar that I am starting to host. And don't forget that I will have this posted. I'm going to have a link that I'm going to send to everyone that registered, and I am going to post it on YouTube. But please, if you want more help and if you feel like you want to continue covering specific methods, follow me on Instagram, follow me on TikTok, subscribe to our YouTube channel. If you have any questions, comment on there. I'm always available, and I'm trying to respond to as many people as I can. And that'll give me more feedback as to what we should cover next time. But anyway, again, I thank you so much for being here. Truly appreciate it. You have no idea what that means to me. And I'm hoping that I see you either next week or in the future. All right, everyone. Hope you have a fabulous end of the week and a good weekend. And I'll see you soon. See ya.